So we're moving into section 5.6, which is about logarithmic equations and exponential equations. So basically equations that have logarithms in them, and also equations that we have exponential functions in them. So we want to begin with, first of all, the logarithmic equations. I'll start off with just exercises. I'll write that word down and I'll say determine the exact solution. Solution to each equation. So when it says exact solution, that means you're not going to plug these into your calculator and get decimal approximations. So sometimes you might get some really weird expression, and we don't want to plug it in our calculator and get an approximation. We want to write down the exact answer mathematically, even if it involves weird symbols. Okay, so number one. We have the log base 5 of the argument's going to be 2x minus 5 equals 3. So we want to solve this for x. Now before I actually start solving, every time I do one of these logarithmic equations, you have to remember that the argument has a restriction on it. There are certain things you can't plug into a log. So we're going to do a restriction on the domain before we even solve it. So restriction on the domain. So what can you plug in for x, basically? So I'm going to take the argument, 2x plus 5. And remember, that has to be positive, or 2x minus 5. That has to be positive. So we're going to say it's greater than 0. So arguments of logarithms have to be positive. So if we add 5 to both sides, we're going to have what? 2x is greater than 5, and then divide both sides by 2. The 2's cancel on the left. You get x has to be greater than 5/2, or in other words, x is greater than 2.5. Now that's not your solution, that's just telling you what x has to be greater than. So if you were to get a solution like x is negative or x is 0, that wouldn't work because that's not in your domain. So you have to keep that in mind. Okay, so we have the domain, that's going to be in the background. We have to make sure that our solution doesn't violate the restriction on the domain. Okay, so now what we're going to do, we're going to start solving this. We're going to start with our logarithmic base of 5 here. Let me put that in red. And I'm going to write what? 5 to the third power equals the argument. To x minus 5. Right? That's how we define a log. It's actually an exponential expression. So 5 cubed equals 2x minus 5. So we're going to do 5 cubed. Which is 125. So 125 equals 2x minus 5. And then we just get the x by itself. We would add 5 to both sides. We get 130 on the left equals 2x. And then we just divide both sides by 2. The 2's cancel and we get that x is 130 divided by 2 is, what's 130 divided by 2? 65. So this is a potential solution right here, 65. The question is 65 greater than 2.5 back here? Does it satisfy a restriction on our domain? Yes, so we can say that's the correct solution. Okay, number 2. let's say I have the log of x squared plus 15x equal to 2. Now remember, when you write log, that means log base 10. So we have the log base 10 of x squared plus, that should be a 15x there. 15x, my bad. X squared plus 15x equals 2. So if I write this in its exponential form, I'd start off with the base 10, raise that to the second power, and that's going to be equal to my argument, the green. X squared plus 15x. Right, that's the way you write that logarithmic expression in exponential form. Now 10 squared is 100. So we have 100 equals x squared plus 15x. And we want to say, well, this is a quadratic, right? This is a quadratic. So remember, when you're solving a quadratic, you want 0 on one side, everything else on the other side. So I want to get 0 on one side. Let's subtract 100 from each side. Whereas we'll get 0 on the left, and on the right we'll have x squared plus 15x. There it is, x minus 100. And you can solve this quadratic by either factoring or the quadratic formula. We are going to factor this quadratic polynomial. We'll make two pairs of parentheses, and we'll ask what times what gives x squared. Well, x times x, write that in. And then we'll find two numbers that multiply to give minus 100 and add to give 15 right here. And you can come up with, let's see, positive 20 and negative 5, right? 20 times negative 5 is negative 100. 20 plus negative 5 is 15. So we have our two factors. We can set them equal to 0. X plus 20 equals 0. X minus 5 equals 0. And we can solve those individually. Subtract 20 on the first one, and we get negative 20 as a potential solution. And on the second one, add a 5 to both sides, and we get x equals 5 as a potential solution. Now remember, I said potential solution. We have to make sure that these don't violate the restriction on the domain. I haven't done the restriction on the domain. I forgot to do that initially. Let's go ahead and do the restriction on the domain. So here, the domain, if you look at the domain, it's what is the domain here? X squared plus 15x. And that has to be greater than 0, right? Your argument has to be positive. Now, if I wanted to graph x squared plus 15x, let's say I had a y equals x squared plus 15x, I could find the x-intercepts of that function. We know that's a parabola, right? X squared plus 15x is a parabola. To find x-intercepts, you set the y equal to 0, and you have 0 equals x squared plus 15x. You could factor out an x, and you get x plus 15. So you set your factors equal to 0. You get x equals 0, x plus 15 equals 0. So you would have 0 as one of your x-intercepts for this function, and subtract 15, you get x equals minus 15. So if I wanted to graph generically this parabola, x squared plus 15x, I'd have a 0 here at 0, I have a 0 here at, well, that's not really well drawn. 0 and 1 at negative 15. So that would be my parabola. And we want this parabola to be greater than 0, right? We want our x squared plus 15x to be positive. So that would be over here on the left side. And over here on the right side, that's when it would be positive. So that's when you're between, when x is less than negative 15. So your solution here to the restriction would be x is less than negative 15, or when x is greater than 0. So that's actually a restriction on our domain. Our inputs have to be less than negative 15, that's to the left of 15, and to the right of 0. So the question is, do our solutions back here, our potential solutions, do any of those violate those restrictions? No, they're both fine, right? They're both perfectly fine dudes. Our first negative 20 works, right? Because negative 20 is in fact less than negative 15. And our second here works, right? X equals 5. X equals 5 is bigger than 0. So both of them actually work. Both of our potential solutions are true solutions. Okay, so that's a little tricky. Okay, let's do a number 3. Number 3, I guess what I have here is the natural log of 5 minus 4x equals negative 1. Now let's go ahead and start this by, before we even solve this, let's write our restriction on our domain. Restriction on the domain is 5 minus 4x must be positive, is greater than 0, right? The argument has to be positive. Arguments of logs have to be positive. So if I were to solve that for x, I could subtract a 5 from each side, and I get negative 4x is greater than negative 5, and then I could divide both sides by a negative 4. So if I take negative 4x and negative 5 and divide those both by negative 4, remember when you have an inequality and you divide both sides by negative, you have to change the direction. So right now the direction is pointing to the right. It's going to point to the left when you divide both sides by negative 4. So the negative 4's cancel. On the left you get x is less than negative 5/4, or negative 5 over negative 4 is positive 5 over 4. In other words, x is less than 1.25. So that's the restriction on your domain. Okay. Now let's solve this. Let's go ahead and solve this. So we got the log base e, right? Natural log is log base e of 5 minus 4x equals negative 1. So I'm going to rewrite this. I'm going to write this as e. Use the definition of the log is raised to the negative 1 power. And that's equal to the argument equals 5 minus 4x. Right, that's the way a log works. It's actually an exponent in disguise. E to the negative 1 equals 5 minus 4x. So I want to get the minus 4x by itself, so let's subtract a 5 from both sides. So that gives me e to the negative 1 minus 5 equals minus 4x. Okay. Now finally, what we want to do is get the x by itself. So we're going to divide both sides by a negative 4. So the negative 4's will cancel, and I'll get x by itself is equal to e to the negative 1 minus 5 divided by negative 4. There's one way to write your answer. Now, if you don't like this e to the negative 1 power, I'm going to circle that in yellow right here. Well, it's supposed to be yellow. If you don't like that, you can rewrite that as 1 over e, right? That's the same thing as 1 over e. So you have 1 over e minus 5 divided by negative 4. That's your potential solution. Now let's actually check. Let's see if that is less than 1.25. So the restriction on our domain here is that your x value has to be less than 1.25. I'm going to plug this in a calculator. Let's see. A calculator. So let me get out my calculator and see if it's less than 1.25. Let me clear out this. Okay. I'm taking, let's see, 1 divided by e. Okay, and then I got minus 5, close parentheses, divided by, let's see if they have a negative 4 here. Yes, that is less than 1.25, right? 1.15803, yeah. So that is less than 1.25, so we're in good shape. So this is actually our true solution here, our true solution. Now, there are other ways to write this, but this is a good way to write it. Okay, let's do a number 4. What's number 4? Number 4 is the log base 3 of x plus the log base 3 of x minus 8 equals 2. Now notice this is the first equation where we have multiple logs, right? We have 2 logs, and they're the same base, which is good. That means we can condense these logs together, right? We can put these together. So one of our properties of log says I can take 2 logs that are added together with the same base, this addition here, I can put them together by multiplying the argument. So I'm going to take the first argument, x, times the second argument, x minus 8, and multiply them together inside of a single argument. And that's going to be equal to 2. So now I'm going to do my definition of a log. We're going to take the base 3, right? Raise it to the right-hand side. So we're going to square 3. And that's going to be equal to the argument, x times x minus 8. Right, that's what a log is. It's an exponential expression. Okay, so now on the left side, I'm going to do 3 squared is 9. On the right side, I'm going to distribute the x. I'm going to do x times x is x squared. X times negative 8 is negative 8x. This is turning out to be a quadratic, so since it's a quadratic, we want 0 on one side, so we're going to subtract a 9 from each side. We're going to get 0 equals x squared minus 8x minus 9. And we can either factor that or try the quadratic formula. I'm going to have 0 equals 2 pairs of parentheses. We're going to do an x times an x to get an x squared, and we're going to find 2 numbers that multiply to give negative 9, and what happened? Okay, find 2 numbers that multiply to give negative 9 and add to give negative 8. So, Apple Crapple is bugging out. Apple crap. All right, so what 2 numbers multiply to give negative 9 and add to give negative 8? Well, you can do negative 9 and positive 1, right? Negative 9 times 1 is negative 9. Negative 9 plus 1 is negative 8. So then I take my factors and I set them equal to 0. X minus 9 equals 0. X plus 1 equals 0. The first one, I'll add 9 to both sides. I'll get x is potentially 9. The second one, I will subtract 1 from both sides, and I'll get x is negative 1 potentially. So what have I not done? I forgot to check my restrictions on my domain. Our restrictions on your arguments. Restriction on domain. Here we have two arguments, right? We have the first argument, so I'm going to have two restrictions. My first argument is x. So number one, x has to be greater than 0. X has to be positive. Now my second argument is x minus 8. So number two, x minus 8 has to be positive. So if I add 8 to both sides on that one, I get that x must also be greater than 8. So my solutions have to satisfy both of these conditions. They have to be positive and they have to be greater than 8. So actually one of these fails. So the 9 is okay, right? 9 is perfectly good. 9 is greater than 0 and it's bigger than 8. But if you look at negative 1, negative 1 right here, that fails, right? Because negative 1 is not positive and it's not. It actually fails both of them. So we're going to throw that one away. That's called an extraneous solution. It's not really a solution. It wanted to be a solution, but it didn't satisfy the requirements for our domain. So throw out negative 1. So you just have one solution to this. Okay, that's number 4. 1, 2, 3, 4. Let's do one more logarithmic situation. This will be number 5. Here I have log base 4 of 2x plus 31 minus log base 4 of x equals 3. So you can see once again we have two logs of the same base, right? We have log base 4 and log base 4, these two logs. We want to condense those together into a single log. And here we have what? Subtraction. So when you have subtraction of two logs with the same base, you can condense them together. So it's the opposite of expansion, it's condensing them. So we can put them together into a single log, log base 4 of, so you're going to take the first argument, 2x plus 31, the one that comes before the minus, and that's going to be, the minus essentially becomes a division bar over x. That's the second argument. So that's all equal to 3. So now once you have those condensed into a single log, you want to write this in exponential form. You want to start off with the base 4. You're going to raise that to the right-hand side here, 3, 4 to the third power. And that's going to be equal to the argument, 2x plus 31 over x. Right? So remember, a log is just an exponential. So 4 to the third power, 4 to the third power is 4 times 4 times 4, that's 64. So we have 64 equals 2x plus 31 over x. And to solve this equation, you would multiply both sides by x to eliminate the denominator of x. So the denominator of x cancels with this x here on the right. And you have 64x equals 2x plus 31. Okay, so then you would get all the x's on one side, so I would subtract a 2x from both sides. And on the left side, I would have 64x minus 2x is 62x. On the right side, I have a 31, and then I would divide both sides by 62. The 62s would cancel on the left. I'd have an x. On the right, I have 31 over 62, which reduces to 1/2. So this is the only potential solution I have. Let's check if it actually works. We want to look at our restriction on our domains. Restrictions on the domain. So we're going to have two restrictions for the first and the second argument. So the first argument here, 2x plus 31 must be greater than 0. So if I solve that for x, I'm going to subtract 31. From each side, I get 2x. It must be greater than negative 31. And then divide both sides by 2. I get that x must be greater than negative 31 over 2 is negative 15.5. So the first restriction is x has to be greater than negative 15.5. The second restriction, so we look at the second argument here, which is x has to be greater than 0. So the question is, our solution 1/2, is it greater than negative 15.5? Is it greater than 0? Yes, it is. It's both of those things.